Hi everyone, welcome to another one of our short video series. In this video, we will learn about total internal reflection and its application. Consider the case when light travels from a denser medium to a less dense medium. We know that it bends away from the normal. This means that as the incidence angle increases, the angle of refraction will increase even more. In fact, there will be a point where the angle of refraction becomes 90 degrees. And when that happens, any increase in the incidence angle will result in the light being reflected back into the first medium. We call this total internal reflection. Let's take a look at the process again. If you look carefully, you will see that as we increase the incidence angle, part of the light from the glass prism is reflected, while most of the light is being refracted. At the point where the light emerges parallel to the media boundary, the incidence angle has been given a special name called the critical angle. Past the critical angle, all the incidence beam is being reflected back into the first medium. Hence, we make use of the term total. And this is to indicate that all the light is reflected back. For total internal reflection to take place, two conditions must be satisfied. The first condition is that light must travel from an optically more dense medium into a less dense medium. The second condition is that the angle of incidence must be larger than the critical angle. Can we apply Snell's law to determine the critical angle? No, not directly. Why? Because Snell's law can only be applied when light travels from a less dense medium to a more dense medium. Therefore, before applying Snell's law, we need to apply the principles of reversibility of light, which says that if the direction of light has been reversed, it will still travel along the same path. So now 90 degrees is the incidence angle, and the ratio should be sine 90 over sine theta c. The next question is this ratio equals to the refractive index of the second medium? And the answer is yes, since the first medium is air. Therefore, we equate the refractive index of water to sine 90 degrees over sine theta c. And simplifying the equation gives us sine theta c is equals to 1 over the refractive index. As the name total internal reflection implies, 100% of the light is being reflected. Compare this to a mirror, which only reflects 90 to 95% of incident light. Therefore, prisms are more efficient at reflecting light than mirrors because of total internal reflection. That's the reason why prisms are more often used in optical instruments such as binoculars or periscope, because there's no loss of light or clarity of detail. Let's take a look at this video. Did you observe something strange? Isn't light supposed to travel in straight lines? Why is it that the laser light appears at the end of the water flow? If the laser light appears at the end of the water flow, does it mean that it is traveling along the water flow? Is light being bent? This is what we call a light guide, and it is used in optical fiber. How does it work? When light is shined into the guide, it undergoes multiple total internal reflection and travels along the guide as shown in the diagram. Optical fibers are commonly used in homes to carry data from the internet to the router. For total internal reflection to take place, the cladding, which serves as a protective layer around the fiber, must have a lower reflective index than that of the fiber. Total internal reflection is also the reason why diamonds are so shiny. Watch this video to understand. The critical angle of a diamond is about 24 degrees. If you think about it, light has a 66 out of 90% chance of undergoing total internal reflection. It is as if light is being trapped inside the diamond, making it shiny. As the light emerges, it undergoes dispersion, giving you a spectrum of colors. That's all for this video. Be sure to check out our other videos.